Okay. Now we consider this exercise and we read the problem. The actual volume, that is the expected volume of a pipette, is measured. Sorry, there is a micropipette whose nominal value, that is the expected value, is 500 microliters. The actual volume, that is the experimental volume, is measured by weighting the volume of the water taken by this pipette. And the data are the same as exercise 1. Calculate the confidence interval of the mean with 95% confidence level, and then assess the trueness. Trueness is the capability to go close to the expected value. Assess the trueness of the pipette with the significance 5%. So here it is asking to us to perform a subjective test, to take a subjective decision. Then assess the trueness of the pipette by calculating a p-value. So it is asking to us an objective decision. Okay? The first part we already know, because we have learned in the previous lesson, but I think it is useful to try to calculate again together. So I click on a one cell, I'm choosing the C9, and I will calculate the average of these 10 values. I type equal or plus. Then I type the name of the function, average. It is listed in the menu, so I double click on the first, the right one. Then I type the cells where the input data is present, so I type E8, column, E17. Close the round bracket and type enter. Sorry. It is A. Sorry. The input values are these ones. So, this is the average value. Now, we calculate the standard deviation of this sample of 10 measurements. Equal STDEV. You see, there is a list of functions. The first one is the standard deviation of the population. The second one is the standard deviation of the sample. We need this one. Double click and then input the vector where the input data is present. So A8, column, A17, close round bracket, enter. Then the number of measurements, so equal, count, open bracket, click left on the mouse and scroll and close the bracket and this is 10. As I told in the previous lesson, these three functions can be also set in order to expect more values. Instead of 17, I could type here 107. So I make it possible to add up to 100 values. And for the others, it is the same. So the standard deviation can be calculated from A8 to A107. And the same for the count. Now I have to calculate the degrees of freedom. In order to give a numerical answer, only one measurement could be enough. But to study the variability, I have to perform more than one. So the number of degrees of freedom is the number of measurements minus 1. So I type equal E8 minus 1. And this is the number of degrees of freedom of this statistical problem. Now I calculate the standard deviation of the mean. We can perform it in one single calculations because we have the T already calculated, you see, in the D20 cell. Maybe we can calculate it again together. Equal T, I, N, D. Sorry. Sorry. T dot I, N, D. This is what now we need today. Okay, it doesn't work, so we go with the menu, insert function. I select the category statistica, and I go down, and the right function is this T.IND.2T. Okay, which is the probability. I choose a significance, usually it is 0.05. It is already typed in this worksheet, in the cell C20. So I click on C20. And then degrees of freedom are calculated in E8. Okay?
No, degrees of freedom, no. It's not E8. It's F9.
Okay. I think that I need more coffee. Alpha is here. I think I have some problem with this software. I have to restart because okay, F8. Sorry, I'm still sleeping. Okay. You see that the number is different, but it is because we have visualized a minor number of digits. The number is this. Look how many digits it can visualize for you. This is the value of T. I think they are finished. Okay. This is the t tabulated, that is the value of t that we use to calculate the borders of our experimental confidence interval. Okay, now we have all the elements to calculate the absolute error of the mean. We remember it is obtained by multiplying t tabulated multiplied by the standard deviation of the sample divided by the square root of the number of measurements. So we insert this formula directly in one cell. I choose the G9 equal. Click on the cell containing the t-tab, D20, multiply by the cell containing the standard deviation of the sample, D8, divide by the square root SQRT, open bracket, the cell where the number of measurements is typed, E8. Close the bracket, and this is the result. The two cells with the average and the absolute error are copied respectively in H8 and J8. You see, in H8 there is the trivial formula equal to C8, so I have copied the average value. And in the cell J8 there is the trivial formula equal G8. I have copied the same value as the one where I calculated the absolute error of the mean. And I have formatted these numbers correctly, because to the absolute error I have left only one significant digit. And since the order of magnitude of the errors are units of micrometers, also the average volume should be rounded to unities of microliters, and rounding them becomes 499. The same result as the exercise of the previous lesson. Now we move on. We want to compare this confidence interval that is highlighted in orange with the expected value that is typed in the cell B8. This is our reference value, 500. What do we need? Okay, we need to calculate TK. That is that value of t that is identifying the position of xk with respect to the average. And so this tk is equal to the absolute difference between the known values, the expected value, and the average value divided by the standard deviation of the average of the mean. In the picture, the names are in Italian. X noto means it's expected, and the TOS observed is the same as TK in the picture. And of course, X in this problem is the volume. Okay, so let us calculate this TK, the value of T that is identifying the position of xk with respect to the average. And we calculate it by this formula So equal. The function for absolute value is ABS, open bracket, and then we put in the difference between xk and x average. So xk is B8, correct me if I mistake, making sense, minus x average is in C8, close the bracket, and this is the numerator of the formula, divided by the standard deviation of the mean is the standard deviation of the sample divided by the square root. So we need a bracket in the denominator because we must type a ratio. So open the bracket, click on the cell with the standard deviation of the sample, B8, divided by S2RT, open bracket. The number of measurements are in E8. Now we have to close two brackets, the square root and the denominator. So close the first bracket, close the second bracket. Okay? The colors try to help you to identify the brackets. I know that Excel is not the best software for typing formulas. Anyway, Excel is the widely diffused software. In my research work, I use a program that is called R. R is a programming field where I can type instructions. In Excel, sometimes with many brackets, it is a bit confusing, but this is okay. So TK is 0.394. This is the distance between xk and x average, calculated using as units as unit of measurement the standard deviation of the mean. So it means that xk is 4.394 times distant with respect to x average, using x average as unit of measurement. Maybe it was not so clear, so I will repeat. Let us round, to be brief, TK to 0.4. Okay, I can round just a moment. It means that starting from x average, I must go ahead 0.4 times the standard deviation of the mean, and then I find xk. This is the mean. I usually express all the numbers with at least 3 digits in order to give an idea of the order of magnitude, but of course there are many digits. And visualizing a minor number of digits does not mean to modify the numbers. The number is always the same in the memory. Okay, now I have to compare TK with T-tab. Because we said, if TK is lower than T-tab, means that xk is inside the confidence interval. So it is okay. Well, I can see by my eyes that evidently TK is less than T-tab. But in the cases where TK and T-tab are very close to each other, the software can decide. And I make the software type the conclusion using a logic function, that is if. Let us type it together. And I'm looking for it in the menu. So go to Insert Function menu icon. Select the category Logic, Logical, and select If. And see the explanation below. Checks whether a condition is met and returns the value or true, or another value is false, if false. Let us click on OK and fill the boxes. The software is asking to us, which test should I perform? And I know that the software has to compare TK with T-tag. So here I type the cell where TK is calculated, B20, and the condition is minor than D20. So I am asking, verify this condition. And the software tells, okay, what should I do if the condition is true? And my answer is, you should type a text. For the text, you use I always forget the translation of virgulette, quotation mark. Quotation mark. Okay. Quotation mark means I am inserting a text. And the text is, the pipette is true. Close the quotation marks. And if false, the pipette is untrue. So, quotation marks, pipette, untrue. Okay. And the software makes this decision. Okay? Of course, the complete answer will be there is no significant difference between the expected value and the experimental value. But this answer depends on alpha. Now have a look at what it happens if I change alpha. Don't change by yourself, simply have a look. I click here, alpha 4.9. The pipette is untrue because my confidence interval is very narrow and it falls outside. So I want to give an objective result, quantifying the closeness of xk with respect to x average, the similarity. And the function is p-value. So type equal p dot. We need the function this, that means distribution. Go and study the distribution and tell me how much of the area is in the tails, corresponding to tk. So I double click on t.this.toTails. And now the software is asking to me, which is the t value corresponding to your xk? And it is tk. So I click on B20. So tk is identifying the position of xk on the x-axis with respect to x average. And then, semicolon, degrees of freedom. They are calculated in F8. Close the bracket. And the p-value is 0.7. Good level of similarity between my experimental value, 499, and the expected value, for 500. Okay? Now you have a good quantity of time to try with the two exercises, pipette and density. The same numbers that you have found in the previous exercises. If you want, we can start together with density. If you want someone who can tell me what should I type, and then once finished with density exercise, try by yourself by the volume exercise, which is more simple. Okay? So I could here type all the names of the cells, but it is easier for me to copy and modify. Okay, so I copy all these, Ctrl C, I go here, paste, and then I modify. D becomes D, double click, select, and change D in D, and here also D uppercase becomes D lowercase. Okay, you see that it has used the same type of character as delta, that is the symbol, you see, symbol,
Yes.
in order to have the normal type, the normal font type Arial. And also the unit of measurement I take there from here. Copy. And here, paste. Okay, it is a good thing if I teach to you how to do that. Okay, do this. Simply delete the previous unit of measurements, and you have the average. You see that in order to go in the lines below, I type Shift, Enter. Sorry, Alt, Enter. I will start from here. Type D, this is density. If I want to go in the line below to type the unit of measurement, I use the command Alt, Enter. Goes a line below. Because if I type simply Enter, it changes the cell. And then there I can type the unit of measurement. Okay? Grams divided by milliliters. So I can do the same in the cell C3. It is already in the line below, so I can type grams divided by milliliters. It is italics, but I want not italics, I change. Then Ctrl C, go in the other cells where all the unit of measurement should be substituted. Okay, so I have prepared the names of the variables. Now I can fill with the formula. You want me to wait, or are you ready? Okay. So, please, tell me what should I type here? I need the average of the sorry? Open bracket.
A4, 2 dots, A18.
A4, 2 dots, A18. If you wanted to preview 100 values, I can type 103. So I have 100 cells that I can fill. Okay? Now close the bracket and enter. There are many digits. If I enlarge the column, I see there are a lot of digits for this number. Now the standard deviation. That's me. I am old. I have forgotten.
Equals S D E
The dot.
It's the dot S.
Okay. This. Okay.
Then open bracket and keep it. A4 colon A13.
Okay. I put 103. So we have 100 cells. And there are many digits in this number. And
Equal count and select.
I am a robot, I am executing.
Bracket.
Okay. Okay, the same as the others. 15 values. Degrees of freedom. Another voice telling me what to do.
It equals N minus 1.
So E4 minus 1, 14. And we also need the T10. Okay, so I insert the column here, click right, insert. Now in the cell G3, the font is a symbol, but I want normal, so Arial. And here I type T10, so T tab. To have tab in subscript, I select the 3 letters, and then I go to the menu font, subscript. So, which is the function?
Equals T dot INV dot 2T, and in the brackets there is the value of. Oh, we don't have here.
We don't have.
But it's.
We can type.
Yeah, we
Okay.
can. So it's 0.09.
Oh, sorry. Okay.
Then the symbol, I don't know how it's called, comma. And the
Degrees
number
of
14, I
freedom.
don't remember the name in English.
Degrees of freedom.
Degrees of freedom, yes.
The name of the cell.
Sorry. Oh, F4.
Okay. Close. Now, since I would like to have this formula automatic, I prefer to insert a cell where alpha is written. So if I modify alpha, I do not have to enter the formula, but it is automatically updated. So I insert another cell, click on H, insert. Now it is a symbol, it is Arial, but I want symbol, and I type A, and it is alpha. So A in the symbol font is the Greek. And here I type 0.05. Then I go inside the formula, previous formula. So I click on G4. I click in the formula bar and I select 0.05 and click on H4. So it will always take the alpha from this cell. Enter. Okay. Now we need the standard deviation, the absolute error of the mean. A little bit more complicated one, not so much.
So it equals the t tag, so G4 is multiplied by the D4 divided by I don't know what it's called.
If you don't know, we go here in insert function and we ask square root. Go. This is. Double click. And now
square root of the number of measurements, so
equal. Okay. Now we have to give to the absolute error a format that displays only the significant digits. And the absolute error is, by choice of the analytical chemist, is to be formatted with only one significant digit. Can you tell me how should I modify this number? What should I do? I am a robot.
Okay. Right button. Format cell.
Number.
Okay. Scientific. And put 0 in decimal places. Okay.
Okay. This is the order of magnitude of the error, 10 to the minus 3. Now, how should I format this number in order to be coherent with the error.
Uh, 7, 8, 7. So we take just the digits. And these are the 10 to
This
the
is
power
okay?
of minus 3 times.
Is it okay?
Yes.
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 This is the result, the confidence interval. Now we want to make the t-test. So we need, let us take the names from here. So I go in the worksheet t-test. I select from B19 to F19. I click on the common copy. I go there. I click somewhere, C10 for instance. And then I can type the formulas. Ticket.
ABS.
Okay, yes. The
The
first step is considering the distance in absolute value.
Okay, so then the average
The name of the cell,
C4.
sorry, the bracket, C4,
Bracket.
C4, I have to check the distance between C4 and minus. The expected, the known value.
B4.
Okay, and then I should close the bracket of the function apps. Then
It's fine.
it is only the difference. Now I can copy this formula to retype it again and go here. The formula is this one. Okay. Okay, let us do a thing. I will copy this formula here. So I can type, sorry, I must use lower, okay, so this is the formula. So we have started correctly with equal ABS, open bracket, C8 minus D8 close bracket. And this is the numerator of the formula, okay? It is this part of the formula. So
now we have to divide it
divide.
by the 4.
We need brackets because we are going to insert a ratio. So sometimes I open and close the bracket so I do not forget the second bracket and click inside to type the formula. Okay? So
D4 divided by square root of number of measurements.
open and close brackets, and the argument is
So it's E4.
E4. Okay. This is the TK. Can you decide, having a look to some cells, which will be the conclusion? Because TK, let us write them with the three.
Excuse me.
TK, yes?
In this formula, in the denominator, isn't it D4 divided?
Oh, sorry.
Okay, yes.
Okay. And now it's still more obvious, the conclusion. Because your TK is 3 and something more than 3. So means that xk is distant with respect to x average more than 3 standard deviations of the mean. More than 3. And now you should compare this number with which one?
We compare TK with theta.
Exactly, so the reference value is this. We can copy here the same, equal that one. Green. Alpha has been already typed here, so here it is equal to H4. Just to have it beside, but the same. Of course it is the same. And I generally display only 3 digits just to make the worksheet to be less full of numbers. Okay, so by eyes I can see that TK is higher than theta.
Yes.
So the subjective decision is
Is that also in this case? No, it's not true.
TK is higher than theta.
TK is higher, so not true.
Okay, so
No.
it's okay. So our experimental density is significantly different with respect to the expected one. Okay? But we want the software to automatically decide.
So, menu, logical. If
Okay? The test.
D70. No, then in my case, so
Okay.
sorry, the cell under TK.
C11 minor.
The tab.
My cell is E11.
Okay.
What to do if true?
Quotation marks. I don't know, we can put, what we have a pipette still, or
It is not a pipette, it is the density.
so that's
Experimental density, not significantly different. Experimental density, not significantly different with respect to expected. Close quotation marks. and then I copy, Ctrl C, and if false, I delete not. I have written in Italian, not in English. And this is the answer. You see, one could say, but with these numbers are not so different, because the difference is 0.01. Yes, but in this case, the standard deviation is very small. So you have a precise measurement. You say like that. When the standard deviation is low, relatively to the average value, we say the measurement is precise. Means that the bell, the Gaussian bell, is narrow. So you understand, if the Gaussian bell is narrow, it is more difficult to fall inside. But if you fall inside, it means that you are very true in your design. And then we wanted to calculate the p-value. Let us move here. The degree of similarity between the average experimental value and the expected value. So we need a function. Okay, open bracket.
Decay value.
C11. Column. Semicolon.
Degree of freedom.
F4. Okay. It is 10 times lower than the 5% level of risk. So it is much lower, very distant. Okay. Now, I invite you to make the other exercise volume and tell me which of the two operators has better trueness when comparing the one who measured the density and the one who measured the volume of the pipette. This is the task for you. And now we put in bracket. Okay, take your exercise, go to the sheet where I have already calculated, sorry. We can delete all the comments that we have added. It was like that in origin. Then we duplicate this worksheet. You go with the mouse on the name, on the label of the sheet, and you click right. And then you choose move or copy. Then you click on create a copy. And for instance, move to the end. This is an exact copy of a sheet that is correct. It is enough to delete the previous values and insert the new ones. So what will I do? I delete the old input values. Delete. Some functions say I am dividing by 0, no problem, because we will insert the new ones. And here I can do copy paste from the exercise, but it is easier to call inside this worksheet the values of the exercise. So I do like that. Do it with me. Click on A8, then type equal, then move to the sheet pipette, click on the first value, enter, and see what it is written now behind the cell A8. It is written, go to the sheet called pipette, that is a mark for identifying, and take the cell A4 from that worksheet. And now, if I copy, I arrived to A13, that was the last, okay? So I have imported all the data of the exercise. And I think that everything is already okay because the numbers were very similar. So the absolute error of the mean is correctly rounded to 6. The mean value is 496, and the degree of similarity is 0.155, so very high. Not so high. It is lower than 0.3. So, from the subjective point of view, the pipette is true. From the objective point of view, the similarity is 0.15, sorry. That is only 3 times the level of risk minimum. So it is not significantly different, but this stating has low robustness. Okay? Now, who is better between the operator density and the operator pipette? Pipette, of course. Even if the trueness is not so strong, at least it is higher than alpha. Okay? So, we have finished the exercise, just a few minutes to conclude the lesson. We started at 2 p.m., we go on 15 minutes and then we stop because otherwise it is too long. And I go back to the PDF. And I recall what we have done this morning and add some space. So, we said that in general, a significant test is a statistical procedure useful to compare quantities. For instance, unexpected quantities with respect to the experimental one, or 2 experimental quantities. Now, suppose that I have 2 students working in my lab, and I give to both of them the task to quantify the volume of this bottle. And they obtain, each of them, his or her own values. So for student 1, we have a certain average value, x average 1, a certain standard deviation, S1, and a certain degrees of freedom, μ1. And the second student obtains x average 2 with standard deviation S2 and degrees of freedom μ2. You understand that comparing these two outputs is more complicated than the t-test that we have observed. Because here we have to compare two averages, so two values of x on the x-axis. Comparing two values on the x-axis is a t-test, but more complicated than the one that we have seen this morning, because we have to consider also the comparison between the standard deviations. And the standard deviations are a measurement of precision. I mean that if a standard deviation is low, we have a good precision. Means that if we repeat the measurement many times, all the obtained observed measures are close to each other. And we are seeing that comparing two values on the x-axis is a matter of trueness. So we know that we have the t-test for trueness, we need a test for precision.
No, sorry, Professor.
Yeah?
I didn't understand. I mean, we said that we should compare the three values of the first operator with the three values of the second. So comparing two values on x-axis is a t-test.
A matter of t-test because the position of the value of x is quantified by a value of t.
Yes, but the problem is that here we have also to compare the standard deviation.
Yes, I wanted to establish which of the two operators is more precise.
Mm-hmm.
And this kind of comparison is another significant test that is called F-test. F stands for Fisher, who was the scientist who developed this test. And it is easier to compare variances instead of standard deviation. Of course, they are equivalent. So, deciding whether the standard deviation of the first operator is lower than the other is equivalent to deciding whether the variance of the first operator is higher than the other. So
with the F-test, we compare the variances.
The variances, exactly. The variances, as the word itself tells to us, is variability. And variability in direct measurements is the error. If the variability is high, we have a high error because we know that the statistical error will be obtained by multiplying the standard deviation by the t. So if the standard deviation is low, the absolute error is low and the precision is good. Now I will make a list of all the main kinds of significant tests And then, okay, we can start discussing the test and go on tomorrow. So, the significant tests, the main, are 4 kinds of tests. The first one, numbers are not useful. The first one is t-test. With the t-test, we check trueness, and trueness is linked to random errors. Then we are going to study the f-test. Which is useful to study for comparing precision. Sorry, today I am sleepy, sorry. Type trueness and type precision. These are, sorry, the random errors. And these are called the systematic errors. Systematic means that all the values are at the same distance from the corresponding true value, systematic. And f-test accounts for precision, and precision is linked to the variability, the random variability of replicated measurements. Then we have the Q-test. The Q-test is looking for outliers. Outliers are values that are very different from the others. So, possibly wrong values. And they are linked to gross error. For instance, I asked you to prepare a solution using some flasks, 100 milliliters flasks, and you choose 100 milliliters for all the samples, and in the last sample you make a mistake and you take a flask of 50 milliliters. This is a gross error. So something that is linked to not paying attention to what we are doing. So this is an example. And then we have the chi-square. Chi is the translation of the Greek letters chi, square. And it is a measurement of normality. That is belonging to a Gaussian distribution. It is normal. A statistical distribution is defined normal when it is Gaussian.
Were discussing, so we didn't chi-square is a measure.
Is a test for checking whether it is true that our measures belong to a Gaussian distribution. So checking whether the distribution is Gaussian. The distribution is Gaussian. Because in general, in analytical chemistry, when we perform experimental measurements, the results follow a Gaussian distribution. But there are some cases in which this is not true. For instance, if I studied the distribution of the marks of the students of the University of Bologna, they are not Gaussian because they do not follow a random distribution. So there is a test to assess whether our statistical sample belongs to a Gaussian distribution. This is the test on normality. We will not study the Cook test and the chi-square. We will start by studying the F test. I just start the basic definitions and go on tomorrow.
Sorry, Professor, just a clarification. I didn't get why we said that comparing the average is a test.
Yes, because if I take the Gaussian distribution of replicated measurements of X, and I wanted to compare two values, for instance, this one and these two, I make the comparison by transforming the X in T.
Okay.
So this becomes a T1 and this becomes a T2. And I have to compare two values of T. Of course, it is a situation different with respect to the one studied this morning.
Yes.
Because there I was comparing an average value with a number. Here I am comparing two average values. Okay? So it is a matter of t-test.
But of course, the fact that we use it to check the trueness is referred to the first case.
Yes, trueness is the closeness of two reference values. Yes, it is correct what you are saying. The trueness is verified when I am comparing an experimental value with a reference value. But it is a matter of trueness also in this case when the first series of results is obtained by an operator and the second series of results is referred to a certificated standard. Because you can have both of the cases when you work in analytical chemistry. And when you are setting an analytical method to measure a variable x, you always need a reference standard. So in that case, it is trueness. Okay? It is trueness when we compare experimentally with expected. Otherwise, it is simply a matter of t-test. Comparing two values of x is a matter of t-test. Okay, the last definition that we start is what is f, the parameter f. Because we have studied what is the parameter tk. F is more simple because it is simply the ratio, fk, it is the ratio between the higher variance to the lower variance. Of course, I am considering the case where the two operators are measuring the same quantity. Okay? So in this case, I suppose that I have given to the two operators the same sample, or I suppose that I take a standard certificated sample whose results are the first series, and I measure with my experimental equipment the second series of values. So on the handbook of the certificated standard, I read that the average value is x average 1, the variance is S1 squared, and the number of degrees of freedom were μ1. I work with the μ2 degrees of freedom, and I obtain the experimental value x average 2 and variance 3. Okay? And I want to compare these two. I take the highest of the two, the larger, and I make the ratio with respect to the lower. So what do you expect f to which range? Which is the range of values for f? Because I put the higher in the numerator and the lower in the denominator. So f k is always higher or equal to 1. So this is the definition that the analytical chemists adopt for the fk. But if we consider all the possible values of f, so I delete this, if I consider all the possible values for f, and I put them on an horizontal axis, and then I put in the vertical axis the probability to find those values. Yeah?
I'm sorry, Professor, just a clarification. But we calculate, like if we have to make a comparison between two sets of measurements,
Yeah.
we calculate the f-test for each set, and we evaluate which is the lower. Oh, okay.
Yeah.
So
which is the lower variance.
Okay.
Okay.
So anyway, the higher variance and the lower variance are chosen between among the measurements of one set of measurements.
And I'm not sure I understood the question.
If
Okay,
we-
these are numbers, and one of the two variances will be higher than the other.
Okay.
And simply I make the ratio between the higher
Okay.
and the lower.
Okay.
Okay, but I can consider all the possible values of f, even when the variance, the lower variance, is put in the numerator. So here, in the plot that I am going to draw, I consider all the possible outputs of this parameter. And what I obtain is the distribution, the statistical distribution of all the possible results of making a ratio between two variances. So the general curve of the distribution is this. But I will consider only the values of fk that fall in the right tail. Because here I am exploring only the right tail. Okay? I hope I have explained well. And the value f equal to 1 is exactly the median of this distribution. That is, the area that I have drawn on the right is equal to that on the left, this that I don't explore, and both of them are 0.5, 50%. So the unity value of this parameter f is such that we have 50% of the area on the right and 50% on the left. I will repeat this tomorrow and start from here, from the f distribution, to reflect on how making a decision about the comparison of the two variances. Okay?
And Professor, which is exactly the systematic error?
Systematic is, I will make an example.
Yes.
I wanted to measure my weight on a personal scale. Have you ever seen a an analogical scale?
Yes.
You have a reference and the scale is moving.
Yes.
Okay? And if I look at the scale directly, it is okay. But if I look from a side, I will see all the weights lower or higher the same quantity. This is systematic. You see, systematic error. All the values that I read are higher of the same quantity with respect to the correct one. This is an example. It is called, I don't know, Italian errore di parallasse. Parallaxis error. This is it clear? Example of, okay, I will make an example on absorbance. Okay, you know what is absorbance?
Yes.
We are a cuvette. In the cuvette there is a solution. There is a beam entering, which has a certain intensity, and there is a beam exiting. Okay? And the first step in measuring absorbance is making zero. Okay? That means that I put nothing in the cuvette and P should be equal to P0. So absorbance equal to 0 when P equal P0. But if in doing my operation of 0 I am wrong, all the absorbance values will be higher or lower of the same quantity. This is systematic. Because all the measurements are affected by the same constant error. This is systematic.
Okay. No, it was just because I couldn't understand the link with the trueness and the systematic error.
Because if you have a systematic error,
of course,
your experimental value cannot go close to the expected, because all your values are affected by the same constant error. All of them are higher or lower of the same quantity. So you will never reach the expected value with a systematic error. Okay? Okay. So see you tomorrow.
yes,
I think that this week